Hi, everybody. This is Team 10 with Kilowatts for Humanity, and we're excited to present to you our end of quarter presentation for the work that we did in winter quarter. I'm Jules, and this is Josh, Jose, and Jessica. Our sponsors are Dr. Peter Dowenhauer and Daniel Nausner with Kilowatts for Humanity, and our faculty advisor for this project is Dr. Burkhard Englert. We want to extend our gratitude for all of their help and guidance this past quarter as we've gotten into the meat of our project. So, for some background, in the 21st century, developing countries are looking towards a sustainable future as they're modernizing their cities and towns. Renewable energy, in particular, is a technology that enables successful, sustainable development. Kilowatts for Humanity, our sponsor, is a nonprofit organization dedicated to enabling renewable off grid energy systems in developing countries. Working alongside KWH, the IEEE Working Group for Sustainable Energy Systems for Developing Communities, or SCSDC, serves as a joint sponsor to empower communities with sustainable electrification solutions. SCSDC's initiatives are focused on practical, community-centered applications that promote sustainability, aligning with IEEE's mission to advance technology for humanity. An overview of our contribution is our project being a microgrid toolkit that's designed to help plan for the long-term impact and sustainability of microgrid installations. The main feature of the tool is a customizable simulation that predicts energy production and consumption, as well as socioeconomic impacts of a microgrid system. It's a web application that should enable system designers to optimize their plans for energy solutions in developing countries. The goals of our project are to have a user-friendly microgrid design tool that is understandable for non-technical users. We want it to have desktop and mobile functionality so that it can be used in the field as well as in planning stages. Our other goal is to guide users through project creation, system input, simulations, analysis, and storage, again, enabling less technical users to engage with our project and engage with these installations. We want to improve the energy scripts because this is an inherited project from a previous team. We were working from some previous code that wasn't always optimized. And so we want to really be able to easily query resource data such as solar irradiance, wind, and temperature based on an input location. And we also wanted to consolidate and improve the code that we did receive to have better simulations moving forward. Finally, we wanted simulation and results analysis. So we wanted to be able to generate graphics and plot different project outputs. We wanted 20-year-long projections, and we want financial impact and analysis.
Hi everyone. So I'm in charge of the front end, which includes designing and implementing the layout of the website. In order to design each page, I draft the layout using wireframes, which is a simple sketch of what goes where. Next, I code that design into the website using React, which is perfect for our project since it is desktop and mobile friendly and compatible with our backend and only reloads necessary parts of the page. In addition, I also ensure that users are easily able to use the website and is accessible for all. This is what the homepage currently looks like. At the moment, only the login and sign up button is connected and working. However, once it is all done, the graph and clicked will lead to a tutorial for first-time users, and the Learn More button at the bottom of the page will lead to an in-depth manual. Next, I will show you what the login and sign up button looks like. It is very easy to navigate between the two by clicking the small green text at the bottom. In addition, the pop-up design allows users to exit out and browse the homepage for more information if they change their mind. To quickly recap, I have designed and implemented the homepage and connected the sign up and login buttons. Additionally, once our users are logged in, it leads to where the scripts are currently being tested. Of course, that will change once the design page is created, since we want to move away from having users upload their own CSV file. My next steps, oh, if you don't mind, thank you. My next steps are to create the homepage for users once they have logged in. This will be slightly different because it will include a section on the side to allow users to quickly return to a project that we're currently working on. Concurrently, I will also be creating the user manual that will guide and answer any questions users may have. Additionally, I will also be implementing a footer for the website and designing the rest of the website, such as the project design page and about page.
All right. Hello, everyone. So for my work, I have been working on the back end, and for this, we decided to use Google Firebase, which is a subset of Google Cloud. The main reasons we decided on Google Firebase was because it is simple to use, easy to set up, and also cost efficient. So we have five main kind of applications within the Google Cloud. We have Google Authentication for sign in and login. We have Firestore for storing any non-file-like data. We have Google Functions, which allows us to run basically back-end functions. We have some Python functions that we use for the simulation and things like that. And then we have Google Storage, which allows us to store file-like data. And then we also are using Google Hosting to host the website. And then, so this is for Firebase authentication. It allows us to make user login and registration easy. So this basically allows the user to create an account with an email and password, and then each user gets a unique ID to sign them in. This provides a secure sign-in as the user's password is hashed and stored in the Firebase authentication backend, so the password is not exposed at all publicly. For data storage, we are using Firebase Cloud Buckets and Firestore. Firestore is a NoSQL database that allows us to store non-file-like data, like a user's email and username. And then Cloud Storage Buckets is a file storing service that allows us to store and serve large files like CSVs and images. And then for running the backend Python scripts on the website, we use Google Cloud Functions, which allows us to run our simulation functions triggered by HTTP requests. And then so for my progress so far, I have set up user and login registration features. There's currently a project selection page which allows the user to add projects, delete projects, and share projects, which is all connected to our database. And then, yeah, like I said, the database is connected to store user information. And then I have also connected the backend scripts to the websites, so you can run the simulation and it will call the HTTP functions and return a response. And then for my future plans, I plan to work on password recovery, security features, and then also getting our website hosted.
Hello, everyone. So I was in charge of the integration of API data for both solar and wind energy. This consisted of first finding an API that had all the data necessary, um, both for solar, temperature, and wind data. Then after finding that, I needed to process, gather the data, and query it to make sure that it was reliable and useful for our project. Um, Additionally, I also had to make sure that the user interface was well implemented so that the user could use coordinates to be able to pull the data necessary from the area in Africa specifically, where they were intending to do the implementation for the energy ZEOS and the simulation calculation. After getting the data, we had to make sure that it was integrated properly into the simulation that we currently already had working from the previous group and make sure that everything aligned well there. So my progress so far, we ended up finding an API and we went with the National Solar Radiation Database. Within this, there was a lot of data sets and we found one that worked good for various locations in Africa. Specifically, we needed data to be retrieved and calculated from Zambia, and we have done that. And the data has been modified to be structured in the same CSV format that the previous group left us. So that was very well done. And additionally, I also had to create a method to fit the user implementation. So the method was to be able to take coordinates from the user and then based off those coordinates, pull the necessary data. And for the future plans, I just need to make sure that the data is reliable. So as of now, we know that the data that we're pulling is accurate, but we want to see the exact model that they use to calculate the data because not every single location has data specifically for that area. Rather, it is calculated in a 4x4 grid. And we're just trying to see what the formula is to kind of get a better estimation of any possible error percentage within each of the values. And then additionally, we also want to make sure that the wait time when pulling the data is reduced. We're doing this by ensuring that the database, once it pulls a data from the API, it doesn't have to do it multiple times over and over. Rather, it just stores it and ensures that the user doesn't have to sit and wait for long periods of time. And then additionally, for our future goals, this is just if we have time after meeting all the MVP specifications for our project. If given the time, we'd also like to be able to include areas outside of Africa, potentially in like the United States or just any other area that could be of use for our sponsors. And lastly, we also want to see if, given the time, we have the ability to allow the user to select what data they would like to be implemented into the simulation. For example, if they only wanted the wind speed, they would be able to query or select it and then just query solely the wind speed rather than pulling everything if for their case it is not necessary, just to make things more efficient for them and to be able to give them a better estimate in the future.
All right, so my main job was consolidating and improving the performance of the legacy code that we inherited. This included solar, wind, diesel, load, and net energy calculations, as well as storage of energy in a battery. The first script that I worked on was solar energy generation. We're using a panel output formula based on principles from physics and electrical engineering that was developed by the previous team. We did briefly consider some other models, including PV watts, which is used by National Renewable Energy Laboratory, or a machine learning approach that would develop a prediction based on pattern analysis. But we decided that would be too computationally intensive and that the current approach provides a realistic estimation of solar power output. And so we wanted to just leave it as it was while improving its output. So it incorporates efficiency variations dependent on temperature and other environmental losses. And it's a little bit more complex than a simplistic model that assumes constant efficiency. Hourly data is the default, and you can see an output example here on the slide. So the equation that we use is the ratio of measured irradiance to the ideal condition. And that's multiplied by the rated power output of the solar panel and the power output of the panel with temperature considered. It also incorporates at the end a product operator of the losses at the end. Like I mentioned, the losses that we're including account for many environmental factors, so as well as electrical degradation factors. So we have wiring losses, module mismatched losses, module aging losses, dust and dirt, as well as conversion losses. Another feature of our simulation is wind energy data. Wind turbines convert the kinetic energy of moving air into mechanical rotation and subsequently into electrical power. And so wind turbine efficiency is heavily influenced by wind speed, turbine design, and control mechanisms that regulate the power output to prevent mechanical damage. The power output of our wind turbine simulation follows a piecewise function, which reflects those operational constraints. So if the wind speed is below the turbine's cut-in speed, or the minimum required speed, basically, or if it's above the cut-out speed, which is the maximum safety threshold, then no power is generated. You can see the value is 0. Between the cut-in and the rated speed, the power output follows a cubic relationship. So the power increases as the cube of the wind speed, which reflects the physics of kinetic energy in moving air. I won't get into the details, but this is a simple but effective model. And at and beyond the rated wind speed, so if the wind is blowing too fast, but not fast enough that we would consider it a safety concern, the turbine produces fixed maximum output to protect the electrical system by never generating too much energy. As always, we're converting our power output to kilowatts for our display. Even our calculations are done in watts. Oh, go ahead. Diesel generators are another feature that we really wanted to incorporate into our simulation. Diesel generators provide a stable and controllable energy source, particularly when renewable generation is insufficient. However, their efficiency is influenced by mechanical and electrical losses, as is the case with our wind and solar before. And these need to be accounted for when calculating the energy output. So our diesel reads fuel consumption and generator output from a data set and applies the losses of engine efficiency, generator efficiency, transmission, and converter losses. And we also have on the bottom there, we aggregate 5 different loads and funnel that into our net energy calculations. Eventually, we might want to accommodate more loads, but right now capping it at 5 is a realistic choice for us. So here's a graph of a net energy calculation. This is really simple, solar plus wind plus diesel minus the load equals the net energy. And this is taken hourly. You'll notice that without a battery system implemented, when the load is high, our net energy much higher than all of the other energy that we're generating, we're just dropping as a reflection of that load in our net energy. But with a battery, we'd be able to store some and you'd see more of a distortion or like a shift of the net energy off to the right. Next slide. Cool. So that's basic overview of what I've worked on so far. There's calculations for solar power, load profile, wind energy generation, diesel energy generation, and net energy balance. I used matplotlib for plotting all of the graphs, and all of the graphs are saved and displayed in the web application. There's also customizable inputs. So for example, your cut-in speed, or cut-in speed, cut-out speed for your battery, or the amount that your diesel generator is generating. But there's more to be implemented, obviously. So next to do is basically modeling battery storage, also improving the user input and web UI enhancements. There's some things that are currently user input and some things that are hard-coded. Adding interactive graphs instead of just plots generated by matplotlib, as well as optimizing the energy mix for different demand scenarios. So for example, if we had a certain demand on our system that's a lot of households, we might want to rely mainly on a specific type of energy. So that's what's next. Does anybody have any questions about the project?